Hello, Mr. Aaron, Mr. Ryan, are you right? Okay, good. So yesterday we talked about finding the shortest path on directed unweighted graph. Okay, directed means the graph has these arrows. Unweighted means the cost between the vertex, if there's edge, is uniform, is 1. We can think of it as 1. This diagram, Freud, is a multi-source shortest path algorithm. Multi-source means that by running the algorithm, we'll be able to find out the shortest path between any pairs of the vertex. So this is a OV cubic algorithm, OV cubic time and OV square space, okay? Because we need a OV square to hold the shortest path between any pairs. Okay, so this is not the most efficient, but it allows us to find the shortest path on a directed or undirected, weighted or unweighted graph. And how about the graph has these negative values, negative cycles? Does it have a shortest path? For example, like this one. Look, 1. This is 2, 3, 4. Okay, and then 5. Okay. So look, this is a directed graph, directed weighted graph. Okay, let's say cost 10 here. -5, 1, 2, 7. So given this directed weighted graph, do we have a shortest path? Can we calculate the shortest path? Look, this is weighted.
Where to where?
So to yeah, good question. From 1 to 5. Look at this directed weighted graph. Do we have a shortest path between 1 to 5?
Yes.
1, 2,
2.
3. You can go to that. Okay, so maybe here. Okay, this is a cycle. Okay, so you can go that way. So look at this directed weighted graph, right? There's no shortest path. Why? Look.
They have a cycle. You could go around.
You can go round and round and round because the cycle. What's the sum of this cycle? -5 plus 1 plus 2.
-2.
-2. Okay, so what does it mean? I go one cycle. -2. I go another cycle. -2. Always shorter distance. If there's a negative weight cycle, then there's no shortest path. Freud is the shortest path that can be applied in directed or undirected, weighted or unweighted graph. And then the time complexity is OV squared, the space complexity is OV2. Okay, V is the number of vertex, or you can say ON cubic, ON squared. Okay. Okay, this graph is directed unweighted graph. And Ryan, you said we can use the breadth search because it's unweighted, right? Because it's unweighted, then we can apply this breadth search. Do you still remember how do we use the breadth search?
Q to Q.
Q to Q, yes, Q. Breadth search can be applied on the graph, right? And then trees are a graph, right? So we talk about that. Tree is a graph. Graph is not essentially a tree. Tree is a very special kind of the graph. The thing about the tree is that we can travel to the children from the parent, but we cannot travel from the children back to the parent. Okay, we can travel from parent to children, but not the vice versa. So that's the key difference between the trees and graph. For the graph, if it's a directed and undirected graph, you can usually travel forwards and backwards, right? Look, if it's a directed or undirected graph, if it goes both ways, look, 1 can go to 2, 2 can go to 1. So that causes a problem. Right? If we use the breadth search or depth search, what problem? We have to remember the vertex. Otherwise, we're traveling between the vertex forever, right? So we use this hash map. Breadth search, the Q, yeah, the Q, BQ. In Python, we're using BQ, double NDQ. Double NDQ means that we can do this pop a pen on both sides, left and right. So on the left hand side is pop left and append left. On the right hand side is just pop and append. And these 4 operations are O1 constant time. So it means that it's better than we using this simple list in Python, because in Python we're using the list like that. Yeah? If it's on the right hand side, it's O1 constant time. If we want to do this operation on the left hand side, it's ON linear time, so it's not very efficient. So we prefer using the DQ. For the breadth search, how do we implement breadth search? First of all, we want to get the shortest path between A and B, right? We might travel some points here, right? Okay, leave here. A. Okay, let's put the numbers. 0, 1, 2, 3, 4. So this is a directed unweighted graph. We want to find out the shortest path between 0 to 3. So at the beginning, we'll put a 0, we include the 0 in the queue, right? And then we take everything out, and we append its kit 1. Then we take everything out, we append its kit. So from 1 we can go to 2, 3, 4, right? So look, 2, 3, 4. Now we have 3 here. We know we have 3. So the distance between 0 to 3, how many steps? 1 step, 2 steps, okay? So we talk about the breadth search. We have 2 ways of taking out the items, DQ, from the queue, right? We can take 1 at a time, or we can take everything out of time. So in this case, we can do both, right? So we can take everything out of time, or we can take 1 out of time. Mm-hmm. Define breadth search. We want to calculate the distance between I to j. At the beginning, look, we have to check. If I equal j, then we just return 0, right? If the source is the destination, there's no point to perform the breadth search. We just return 0. Then q equals dq. At the beginning, we put an I in it. Now we have at the beginning the distance will be 0. Right? So while q, before that we need to have a scene equal set. We want to remember the vertex we have visited, so we don't visit it again and again. While q, this is the same as the checking if there are elements in the queue. It's the same as y length q or length q bigger than 0. Okay, this is the same thing. Every time we take everything out of the queue, then the distance will be incremented by 1. So d plus equals 1, and n equals the length of q. This is the number of the nodes that in the next level. So for n, we need to take n items from the queue in range n. C equals q dot poplet. We take the 1 element from the queue. Then for x in GC, GC means the vertex that connects to C. So if x not in scene, right? We haven't visited the scene. The first thing is to put it in the notebook at x, right? And then q dot append x. So C equals q dot poplet. If at this point we find out that it's j, then we need to return, right? So we need to add that here. If C equal j, then we need to return d minus 1, right? Because we have already plus 1 here. If we can't find the j, when we do this breadth search, we need to return 0. The cost is 0 or infinity, depending on the requirement. So this is the breadth search. So we are taking everything out of the queue. So we can use this d to compute the cost, the number of steps. Right? So when we find the j, when we find the destination, the d will be the distance. If not, if we take 1 element out of the queue, we have to put a tuple. We have to remember the cost by the vertex, so we can push the like I, and then the cost will be 0. When we do this in queue, putting item back to the queue, we need to increment the cost by plus equal 1. This is another approach, okay? Let's breadth search. Any questions so far?
Not really.
Okay, so what have you learned today? What's new?
About the breadth search, about finding the
shortest path, right? So
in the unweighted graph.
Unweighted, that's very good. Yeah, for the unweighted graph, we can use the breadth search. But if it's a weighted graph, we cannot use the breadth search. For the weighted graph, we can use the uniform cost search, or we can use the Dijkstra, or we can use Freud washer. There are quite a few different shortest path algorithm. Maybe different scenarios we can apply each algorithm to. Okay, the graph algorithm is quite useful. Real life application can be visualized, can be modeled as the graph problem, and we can find the shortest path. Right? We can find the shortest path. Okay, that's it. Bye bye. Bye bye.